what we will continue on today is amortized analysis. We will see one interesting example of a data structure that utilizes amortization to enhance access to the data that it stores. Splay trees are a class of data structures that are called self-adjusting. You have seen before in the database course the B+ tree, which is also a self-adjusting tree. Now, splay trees is a very interesting data structure because this is not a self-adjusting binary search tree. It's not just that. It has this very interesting property that gives you access to the more frequent accessed elements faster than the less frequent accessed elements. Now, what that entails is the tree reorganizing itself after each access to make sure that the one element you just accessed will be accessed faster in the future. This operation that we're referring to here is called splaying up the tree. So this splaying operation involves changing or readjusting the tree, and along the way introducing some balancing effect on the whole tree with every single operation on the data structure. So whether you're doing insert, find, delete, find minimum, any operation that you will support on the splay tree, after you do the operation, you will invoke an operation internally called splay. And this is where amortization will happen. The worst case time for insertion, deletion, and search is O of n. But the amortized performance of the splay tree is O of log n. So as you run the operations, as you store data and run the operations in the splay tree, and you keep running it, your average performance is going to be log n instead of n. So there are many operations that are supported on splay trees, including search, finding a predecessor of an element, finding the successor of an element, the maximum, minimum, insert, delete, and join. All of these guys will end up being amortized log n because of the splay operation that I've introduced in the previous slide. Here is an example of a splay tree. Now, notice that this is a type of a binary search tree. This is a self-adjusting binary search tree. What that means is that the invariance for a binary search tree still holds with us here. All elements to the right are greater than the parent, all elements to the left are less than the parent. At most, because this is a binary tree, at most we could have 2 children per parent. Now, so if you inspect this tree, you will notice that the invariant holds for the binary search tree, and the invariant holds for the being a binary tree. The 10 is greater than the 8, 11 is greater than the 10, so it's placed to its right, 12 is greater than the 11, so it's placed to its right, 13 is less than 15, so it's placed to its left, but it's right of 12, and so on for the rest of the tree. Now, the interesting thing about splay trees is not finding a value, because you will proceed the same way you actually have learned with binary search trees. If I'm looking for a 12, if 12 exists, I will start from the root always. If 12 exists, it will be to the right of 8, so I go to the right child, which is 10, and then this is not what I'm looking for. If what I'm looking for exists, it will be to the right of 10, so I go down again, one level down to 11, and then I go one level down and I find the 12 I'm looking for. Okay? Same thing, if I'm trying to delete the 6, I have to search for it. So if 6 exists, it will be to the left of 8, so I go from the 8, I follow the left child, I go to the 3, while 6 is greater than 3, so I follow the right child to the 4, and then I will find the 6. So we're following the same logic of a binary search tree in all operations, except what is new with us here is the effect of splaying. Let's say we were about to insert 14. In the regular binary search tree, the way it works, you find the location and you always insert the new entry as a leaf in the existing tree. So I will look for a location to insert 14, I will start from the root. 14 is greater than 8, I will go to the right. 14 is greater than 10, I will go to the right. 14 is greater than 11, I will go to the right. 14 is greater than 12, I will go to the right. 14 is less than 15, so I will go to the left. 13 is less than 14, so I have to insert 14 to the right of 13. As far as what I'm just explaining, this is a binary search tree. But notice what's going to happen next. What will happen next is display operation will take effect, or will be invoked basically. So typically in a display tree implementation, you would have a method called display, and you give it a specific node and the root of the tree, and it takes care of displaying the node that you have passed, you've indicated, all the way till the root. Now, in this case, obviously, I will pass the 14. Why? What we do with in the display tree is that after every operation, we display. Okay, it's not an option, and it's not in a specific operation and not in another one. All the operations that you have supported for the display tree will have the last line in the code, invocation of display method. So I'm showing you here the insert. With a binary search tree, we'll just keep the 14 down there. But with the modified, this binary search tree that's called display tree, what we'll do after we do the insert, we display up that value. Display means play it upward and make it the root. So what will happen is I will use a rule, it's called a rotation rule, to move the value up, because I can't just take it upward in any random fashion. I have to respect the binary search tree invariant, which means I have somehow to rotate the value I'm displaying, which is the 14, upward through the parent. Okay? And this is exactly what you see here. The 13 became the child of 14, but to be the right child, it has to go to the left. And 15 became the right child of 14, but to be the right child, or to be the correct placed child, it has to be to its right. And 17 was connected to 15, so it's still connected to 15. But I don't stop there. I'm referring to the second figure at the top row. I'll move on the 14 upward even further by rotating it through the 12. And then I will also rotate it through the 10. And finally, you see the tree at the bottom right, where the 14 has become the root. The effect of displaying the node we're working with is that, since this is the most accessed node, or the most, let me be very specific here, the most recent accessed node, if we are looking for it later on, we will find it at the root. Okay? So, we say that display tree is a type of a data structure that actually has some kind of memory. It remembers what was going on before. And because it remembers, it will actually push what was being manipulated before, the node that was being manipulated, it will push it towards the root. And it will always do that for the nodes that are more common, so the final effect is that the ones we access more will generally propagate upward towards the root, and the one that we access less will propagate downward towards the leaf level. So let's understand how exactly displaying works. I just told you briefly in the previous slide, we're going to rotate, but actually there is a systematic way of doing these rotations. Okay? So we have 3 cases. And in every level, the code will inspect which case we are at, because we could see the 3 cases as we go from the root, the leaf level, all the way till the root. In every one of the 3 cases, we will apply a different type of rotation. The first case, X, which is what I'm interested to display, is the child of the root. This is what shows up on the left image over here. X is the child of Y, and Y is the root. So I'm going to do what's called a simple rotation. And in this case, I will rotate X through the root. Meaning by that, I will make X the root and Y the child of X. And since X was to the left of Y, when I rotate it through Y, I will make Y its right child. And that's what you see on the image on the right. X became the root. X is what I'm interested to display. And since it's the child of the root, I will rotate it through the root, which means I will bring the root down and bring X up. I have to make the proper connections here. And I mean by the proper connections, the children of those nodes. Y had two children, X and C could be a whole subtree. So if I take X up to be the root and make Y the right child of X, at most, remember, I can have two children per node. So since I'm going to make Y the child of X, I have lost a place or a reference to point to B, the B subtree. So I'm going to cut it from X because I'm going to put Y as the right child of X, and I will connect the B subtree to be the left child of Y. And that's perfectly valid because all the entries in the B subtree must have been greater than X because they are to the right of X. And in the same time, they are to the left of Y because they are less than Y. So I can grab all of this subtree and put it to the left of Y, and they will still be less than Y, and they are less than Y, so the binary search tree invariant still holds. And I have solved the problem that I have, at most I have two references, and I'm using one of them in X to point to Y, and consequently I cannot point anymore to the B. So I'll just move the whole subtree to be the left child of Y. Okay? Now, this is called, right rotation because we are going towards the right. Okay? We are rotating towards the right side of the slides, if you'd like. Okay? It's called right rotation at X. Okay? Or you could describe it as a left rotation at Y, as the direction of the arrow indicates. This is the first case, and this is a simple case. Okay? We just have to figure out where to connect the right child of X, and we're done. And the same, what I'm describing here could be applied if X was the right child of Y. We would still rotate X through Y, but then we're going to take one subtree, one child of X, and make it the child of Y, which is kind of the mirror image of what I have been describing. The second case is X is the left child of a right child, or X is the right child of a left child. Okay? So basically here we have different children order. If X is the left child of a right child, or X is the right child of a left child. So let's look at the bottom left image so you understand what do I mean. If you look at X, it's the right child of W, but W is the left child of Z. This is what I refer to as X being the right child of a left child. Okay? We could also see the different scenario where X is the left child of a right child. So whenever we have alternating left and right, child and parent relation like this, we're going to do an operation that's called zigzag or zag-zig, depending on which of the two cases, left of right or right of left. Now, zig generally refers to rotating left, and zag rotating right. So zig-zag means rotate left and then rotate right. Zag-zig means rotate right first and then rotate left. So let's see a zigzag operation. Because X is the right child of a left child, I'm going to do zigzag. Now, again, zig means rotate left, which means rotate the X towards the left. So I will rotate X through W, bringing W downward and X upward, solving the problem of the B that is the left child, which is the left child of X. I will make it the right child of W, just as we've done in the previous slide. But I will not stop. I'm doing here two rotations. The second rotation, it's going to be a zag, which is rotating right. So I will rotate X through Z. This is what you see in the middle image. The effect of doing the zig alone, which is the rotating left, is seen in the middle image. Now, or in the middle figure. Now, after I do a zag, which is rotating right, I bring X upward because I'm going to rotate X through Z to the right. So I will bring Z down and x up, again solving the problem of the subtree that I will disconnect from x, which is c, by putting it the left child of z. And if you notice now, the binary search tree in the rightmost figure looks really nice. It's balanced. And this is actually the effects of these, what you think of as plays or pulling up a node. What we're doing is we're not just pulling it up along a straight line, we are redistributing subtrees that exist along the way to left and right, which means that we are going to decrease the height of the tree, introducing a balance gradually. Okay? It is not the effect of just one simple operation, it's the effect of many simple operations like this that will ultimately help us in reducing the size of the tree or the height of the tree, and we come close to log n. Now the third case, I think by now you got the idea. This is going to be x is the left child of a left child or right child of a right child. And in this case, we're going to do zig-zig or zag-zag. Again, zig means rotate left, zag means rotate right. Okay? So if you look at the figure at the bottom left, x is the left child of y, y is the left child of z. So I will rotate x through y. Did I? No, wait a minute. There is something here you have to always remember. When we are talking about left over left or right over right, we are going to rotate through the parent first. Okay? So, which means I will rotate the parent first, through the grandparent. So I will rotate to the right, y through z. And that's what you see now in the middle figure. Y has been rotated through z, solving the problem of c by moving it to the left of z. Because already y will have x and z as children after I do the rotation. And next I rotate x. So I will take x upward by rotating it through y. Okay? Now, this is what's called a zag-zag, because I rotated right twice. I could also see a scenario where I'm doing zig-zig. Okay, here I'm doing zag-zag, I'm rotating towards the right because it's left over left. So if you think of it conceptually, you know, if the node is left over left, there is no way you can turn left because there is nothing left of you, okay? The node is left over left, so its left is empty. So if you rotate, you have to rotate right through right, okay? And if the node is right over right, you cannot rotate right because there is nothing there, but you can rotate left, left, okay? And again, on the long run, this operation will enable us to actually reduce the height of the tree to be close to log n or log n, you know, an amortized log n. So let me show you the effect of doing a splay on this skewed binary search tree, which is a typical, you know, worst case scenario for a binary search tree is if we get the values sorted in either order, ascending or descending. So here I would get the 10 and then I get the 9, so I insert it to the left of the 10, and then the 8 I will insert it to the left of the 9, and then the 7, so I insert it to the left of the 8, and this keeps going on until I get the 1, I insert it to the left of the 2, and now I have this skewed binary search tree whose performance is O of n. Now with a splay tree, this problem will be fixed. So while we cannot fix it in binary search trees, in the regular binary search trees, it's fixed over here and we'll go back to log n. So let's do this. Now the last entry I'm going to insert is going to be the 1. Now obviously what I'm describing here is a bit incorrect in the sense that I will never see this type of organization in a splay tree because after every operation I'm splaying. So I will never see this kind of linked list, a skewed version of a binary search tree. Okay? But let's assume that this is what I have. And let's assume this is skewed. I mean, it is skewed. Let's assume that we're going to splay now. So let's just, to study the effect of splaying on an extreme example that is quite unrealistic for a splay tree because you'll never see it this way. But let's see, we just would like to splay on an extreme case, okay? Now, let's play. 1 is left over left, so we're going to rotate right. And remember, when we have the same relation between the parent and the grandparent, so we are going to start with the parent through the grandparent. So I will rotate 2 through 3 and then 1 through 2. Okay? Now that's what you're going to see. And then 1 is left over left, so I will rotate 4 through 5 and then 1 through 4. So this is what you're going to see. And then again, 1 is left over left. So I will rotate 6 through 7 and then 1 through 6. So this is what you're going to see. You see how much the tree has suddenly collapsed into a shorter height, and not just shorter height, it's actually getting very quickly to be balanced with another number of additional splays on any other value except for the 1. This will become even more balanced. Okay, so if I try to splay 4 or 6 or 8, it will become even more balanced. So this is the effect of splaying. We are reducing the height of the tree and we are approaching slowly a log n performance. Now, and this is actually what I did. I tried to here to splay 3, and now you see what's going on here. It's now looking like a decent binary search tree to some extent, you know. And even if I keep splaying, within few operations, this is going to be very close to being balanced. Okay. Now, notice also here that when I splayed 3, the 1 is still close to the root, and this is why we often say that a splay tree has memory. In other words, it remembers who has been accessed frequently, not just the last one. It will look to you at first when you look at it, when you study it, that since we're always playing the node we're working with, then and we place it at the root, then this is the one that the data structure remembers. And this is not entirely accurate. What actually we are doing, we are splaying for sure the node we're working with to be at the root level, but what also happens along the way, because we don't do extreme reorganization of the tree or extensive effort in reorganizing the whole tree. We're just following the path from the node that we are splaying up towards the root. The ones that were pushed earlier up towards the root, like the 1 in this case, and all related entries, are not going to be far from the root. So overall, you could imagine that the splay tree consists of, you know, horizontal sections wherever those nodes at the same level or in the same section have been manipulated recently or more recently compared to the section below them or the level below them. Okay, so generally the values that we work with more will stay closer to the root, and the values that we kind of ignore completely and never access will dive down towards the leaf level. Now, the kind of operations we're going to look at, or that is typically supported in a splay tree, we have the search, which is to find a node containing key x, okay, using the typical binary search tree, just like what I described before. And then after we search, we splay that node once we find it. If we insert, we will do the same thing. This is the example we have seen before with the 14. I insert a value in the right place and then splay it up again. Okay. Now, even for the delete, when I delete a node, I will find the node x. Obviously, I need to delete it. Okay. What I'm going to do is, I will find the node I'm going to delete. I will splay it and then delete it. Okay. So when I delete it from the root, now I have 2 subtrees. So I'm going to go and find the node with the largest key in the left subtree and splay it up and join it to the right subtree. So again, I'm doing splaying even in the deletion. Okay. So again, I'm actually doing here 2 splays, not even 1, because if I would like to delete node x, I will find it and then splay it and then delete it when it's at the root. And then now I have 2 subtrees, I have to join them. So either I go to the left and pick the rightmost, the largest value, or go to the right subtree and pick the smallest value, which is what you learned before was binary search tree. We'll go right all the way to the left, and then what we do is we will take this value, okay, and then we will splay it and then join it at the root. Okay, so we are doing actually 2 splays here. So in terms of performance, as I mentioned before, the worst case time for insertion, deletion, and search is O of n, okay, or close to O of n. It will never be skewed as much as we have seen it with the previous example where the numbers were sorted from 10 to 1, but it's going to be close to O of n, so we'll consider it O of n. But the amortized cost, which is the one really we care about, because that will be just an instance where it's very close to O of n, or an n basically with some small constant. But the average case on the long run, because of the fixing we are doing all the time, is going to be log n. Okay, so the amortized cost for all its operations is log n. The nice thing about this compared to a binary search tree is that this is amortized log n. You could not claim that on a binary search tree. In a binary search tree, the worst case is actually O of n. It's just O of n. You cannot argue about it. You know it's O of n because if you get the numbers in descending or ascending order, it's just plain O of n. Okay. Now over here, the worst case is log n, but it's an amortized worst case. Okay, and we will see why that is and how to reach to this conclusion. So we're going to use the accounting or the banker method to answer the question, what are we saving and what are we paying? Let's look at these four figures of some splay trees. Each one is a separate data structure. They're all splay trees. I'm just focusing on the node that has the 14. If I'm splaying that, the question is how much I'm going to pay. And I will measure my payment here by the number of levels I have to climb upward to reach to the root. So if you look first at the bottom right splay tree, the 14 is actually at the $0 cost because it's at the root. It will cost me $0 to actually move this thing because I'm not going to actually do any movement because it's already at the root, and the goal from splaying is to bring the node up to the root. So if it's already at the root, then I'm not going to pay anything. It's going to be costing me $0. If you look at the other extreme, which is the splay tree to the top left, where the 14 is at the bottom of the splay tree, I will climb up 6 levels to bring it up to the root. So if I'm paying $1 per level, I will actually have to pay $6. And the other two splay trees are having the 14 in different locations, and again the cost is associated with the number of levels. So if you look at the top right tree, I will have to move the 14 up 4 levels to be at the root, so that will cost me $4. And at the bottom left, I only gonna pay $2 to make the 14 the root because I will climb up $2. So what we are saving and what we are spending is related to how far are we from the root. The worst case is to be as far as we can as possibly are from the root. Basically means we are at the leaf level and we are further away in terms of height than any other node except the nodes that exist on that same level from the root. And the best case is if we are actually at the root level. So if we're trying to think now of actual cost and amortized cost, obviously here the actual cost is going to be 0 in the best case, and in the worst case it's going to be $6, giving this specific tree. Okay. Now in the general case it's going to be the log of the height of the tree, because if this is always balanced, because that's the effect of splaying or semi-balanced, then this will have an approximately the height of log n, or n is the number of nodes. So I will move it. The $6 is proportional to the log n, which is the height of the tree. That's the worst case. Okay. So in other words, when I'm actually at the root, I'm saving, if we adopt this convention or these numbers specifically, I'm saving $6. I will pay $0 and I will save $6. If I'm at the $4 scenario, then I will pay $4 and save $2. And if I am at the $2 scenario, then I will pay $2 and save $4. Okay? This is the essence or the merit of how do we think of saving money and spending money. The amount of money we save is related to how much we didn't travel, which means how close we are to the root in relation to the total height, which is log n. We will come back to this concept in the coming slides as well, because we're going to use this idea. So let's start the analysis of splay tree operations using the banker's method. What are the parameters we have? I'm interested in displaying a node, some node x. So I have x being the node I'm interested to display. I will talk about that and I will measure things in terms of that. What am I going to measure? I will talk about the height or the number of nodes in the tree who's rooted at x, because the number of nodes is proportional to somehow the height, because this is a binary tree. So if I say a node has or the size of the tree that is rooted at x, or that is rooted by x, the size is 3, then it will have 2 levels, x and 2 children. If I say 4, then it will have 3 levels, x, the children, and 1 more level for the 4th child. If I say 8, if I say 9, if I say 10, so the number of nodes that x is rooting is significant as a parameter in our analysis, because that will imply certain height. Okay? Now, the critical scenario we have here, we have one critical scenario. Remember, in the accounting method, in the banker's method or the banking method, we have to work on critical scenarios, because we cannot assume or predict what could have happened before. So I'm just going to do the analysis at the point where the critical scenario is happening. What is the critical scenario here? X has just been displayed. What are the assumptions? Display tree has no duplicates. I just want to simplify my analysis. Okay, display tree is already balanced, and this is a fair assumption. Some of you might say, well, we have seen examples where it's not turning to be quite balanced, and the answer is yes. But if you have been running for a while, and I'm not really going to care about how long I've been running, and I'm not going to analyze how much time I've been running, but if you have been running for a while, it will be balanced. You have to believe that the effect of splaying, as we've seen several times, is it introduces balancing very slowly but very surely into the binary search tree. So it's going to be already balanced. Okay. Also, I'm not going to deal with special or biased input. An input where there is a bias in the data that's getting passed, with the intention of affecting the already balanced display tree. Okay, because we could think of combinations of inputs one after the other, insert certain values, given a specific binary, a specific display tree that will affect the balancing, and we will start to see skewness. But again, this will be just for a short period of time, because as we keep playing, we will balance it again. So I'm not going to really be concerned with the very special cases, okay, where the input intentionally unbalanced the tree, because I know it's going to be ultimately balanced by further displays. So let's go to our observations. Rotations have two important effects. They move the node being displayed upward in the tree, we already have seen this, and they shorten the path to any node along the path to the display tree. The second one might not have been that clear to you from the earlier example, but let's see it again. This is the 14 example. After inserting the 14, and I will display the 14, and the final location of the 14 appears in the right figure, where the 14 is sitting at the root. But notice that all the nodes that were on the path from the 14 to the 8 in the left figure also got pushed up a little bit upward. Like for example the 15 and the 13 and the 17, they all moved up, because the effect of splaying is that we are not just taking one node and pumping it up, ignoring everything else. We're trying to respect the invariant of the binary search tree of the right and left child values compared to the parent, and that means these rotations are made to make sure that the invariant holds, but these rotations as well means that you're going to grab subtrees with you along with the node that you are splaying upward. Okay, like for example here the 15. Okay, 14 was the left child, was the right child of a left child. So I rotated left and then right, and then I kept doing that, but along the way I was dragging the 15 upward with me, okay? Because of the notion that we disconnect and connect subtrees to be able to connect another node that we are splaying through it by bringing it down and bringing the node we're interested in up. So this connection of subtrees, or disconnecting and connecting subtrees, will end up taking things upward with us. Okay. Now, so this is one observation that is a little bit subtle. Now, we also have an observation here that splaying tend to make the tree more balanced. We have talked about this several times, and I've showed you here an example of this when we started with an O of n kind of axis set of elements, and if I apply the splaying concept to them, I splayed 1 and splayed 3, and as we have seen in the previous example where we discussed this became quite balanced compared to what we started with. You know, instead of 10 levels, now we have 5 levels in the tree. Another observation is that we are splaying in each of the 3 operations we are analyzing: the add, delete, and find. And for the same input, we're going to do more or less the same number of splay operations for the same input for the same tree, okay? Plus some number of comparisons and pointer manipulations. So basically, if you think of, as an example here, if you think of splaying the 14, whether I was adding the 14, deleting the 14, or finding the 14, the number of splay operations are all very close, okay? We don't really have a difference between the performance because of the nature of the operation. There is a slight difference, of course, when it comes to the delete, because we're going to splay twice, but even that, the number of comparisons we are making and pointer manipulations is very close to the add and find. So we will consider that all the time we're working with a constant number of splay operations for any given specific tree configuration. Now, another observation which we discussed earlier with the slide that I had where the 14 was in different locations, that the node I'm splaying could be anywhere in the tree. However, I can compute the maximum to charge for any operation based on the height of the tree. So the maximum is that the x is at the bottom, which in the case that shows in the figure in the left bottom of this slide. So if x is at the bottom of the tree, that will be the largest amount of money I will pay, and that is actually the floor of log n. Okay? So I will call that mu of r, where r is the root node of the tree, or mu of the root. Okay? Now, in this case, n is the total number of elements in the tree. Okay? But that's only in this specific case because 14 is way at the bottom, and I would like to splay it way at the top. Okay? This is why I say here to splay 14, you're going to pay the most, taking it all the way up, and that is related to the height of the tree. So basically, I can talk about my amortized cost here being the dollar sign, floor of log n, or floor of log n dollars, or simply mu of r, being the largest amount I will ever pay. Now, here is the most important observation of all. When a node moves up because of splaying, the next time we splay it, it will either go up and down. Okay? Now, obviously, if it's the root, it will not go up. And if we're splaying it, it will not go up, it will stay in place. It will still be the root. But if you think of splaying successive series of values where the values are different from each other, like we splay 5 and 10 and 15 and so on. Now, if I splay 5 first, I will take it from wherever it is to the root. The next time, say I will splay 10. Okay? Now, when I split 10, for sure 5 will go down at least one level because 10 will come in its place, become the root. Okay? Now, what that means is every time I move a node up, I am saving moving it up later on. In the case of the 5, this was an extreme example because if I take 5, if I split 5 and it becomes the root, then the next time I will never be able to move it up. If I split 10, it will move down. Okay? But if you think of the fact that when we splay a node, all the nodes along its path from that specific node we're splaying to the root move slightly upward, that means we are making all of them closer to the root, which means we are making them easier to move or less expensive to move later on because we've just pulled them up a little bit as we splay the node we're interested in. So for any given node, if the node moves up, we are saving money where we're going to pay if we later decide that we would like to move it even further up. Okay? And let's say I had this sequence of axes 5, 10, 5. I split 5, now it's at the root. And then I split 10, now 10 is at the root and 5 is close to it. When it comes, now the third operation is to split 5 again. Well, 5 already was close to the root. So my previous operation of splitting it is benefiting me in the next time I try to split it because I'm not going to pay a lot of money. Okay? So the rule is, if a node moves up, we're saving money because we're not going to pay splitting it, or when we want to even push it further up, we will not pay money because we already pushed it up. Okay? And if it moves down, we're losing money because we will need later on to bring it up, and that costs money. Okay? So here the saving is how far the node is from, or how close the node is to the root. The closer it is to the root means the more we're saving. Now, this is the consolidate the idea. Let me read these lines. It says, we said the node x can be anywhere in the tree. If it is at the top, we pay nothing. If it is at the bottom, we pay the most. Now, since restructuring the tree is happening with every splay, same x will be moving up and down continuously with every splay. Now, this actually complicates the analysis, but we will see how we can handle this. Because the thing is, for any given node in a tree, it will always be going up and down. Okay? For any given node, for any given sequence of operations, any given node will be going up and down, at least by one level. If it's on the path from the node we're splaying to the root, it will go up more than one level, most likely, if the tree has considerable depth. If it's not on the path, it either will go, most likely it will actually go down, depending again on the structure of the tree, okay? But either it will go up or down one level. So if you'd like to imagine it, it's like all the nodes are jumping up and down, up and down, up and down, with every splay. And since we're doing a splay after every operation, then all operations are causing all nodes to go up and down at least one level. Some will go even more than that, but at least one level. Okay? So the thing is, every time we go up, we can deposit money in the bank. The difference between it staying in its place and us wanting to move it up, the next time, we're not going to spend that money because we already moved it up. And every time it goes down, we have to take money from the bank. Because this means if we try to split later on, we'll have to actually spend that money to split it up. Now, since we're concerned about x, I'm going to talk about the subtree rooted at x. Okay? So I will maintain a bank balance with every node, and instead of for the whole tree, I will assign a bank balance. I will create, as if I have an ability to open bank balances, I will open a bank balance for every node in the tree. Okay? And I will deposit in that bank balance floor of the log of the tree or the subtree rooted at x. Okay? So if you look at the figure on the bottom right, I will open a bank balance for every one of the nodes. And the content of that bank balance is the height, the log of the height of the number of elements in that subtree. Okay? So for example, the node number 7 has bank balance 0. Why? Because I'm not saving anything by having it in that location. I couldn't have saved anything by having it in that location if I just opened the bank balances, of course. There could be history that enables me to do some savings, but I'm assuming now I'm just creating the bank balances. So 7 obviously will be assigned 0, okay? However, 6 is different. The node 6 has climbed up 2 levels from the leaf level. So that actually is a saving for me if I would ever like to place 6. The node 10 as well has more dollars because that has climbed way up towards the root. So if I like to splay it, I will just move it 1 level up and I will be saving the rest. Okay? Now, this is what I try to highlight here in the third point, that node X always has at least mu of X credits on deposit, where mu of X is the floor of log of the number of elements in the tree rooted at X. Okay? Why? Node X moved up to that height, and with every step up we save $1. We would have had to spend it otherwise to bring it to that location in the tree. Okay? So the height is telling us how much we saved before. Next, we will assume that I operations were executed. We're not going to make any assumptions about what are those I operations and whether they were fast or slow in the 3 operations we are considering. And we're going to do the analysis for the 3 cases: a simple rotation at the root, a zigzag or zag-zag in one case, and a zigzag or zag-zag in another case. So let's start the analysis. Now, in the case of the simple rotation, let's refresh our memory here. We are 1 level away from the root. So we are rotating X through Y to make X the new root. Okay? Now, notice what happens here. The 2 nodes that are changing are X and Y. So I'm going to let mu of X is the initial credit associated with X, and mu of Y is the initial credit associated with Y. By the way, we're doing this after, displaying of X. So this tree has been around for a while. There has been many operations, we don't know how many, and as X was being pumped up or pushed down, we were accumulating dollars, or we were removing dollars from its bank account, and the same thing for Y. But what we are focusing on now is just the changes to X and Y bank balance. So I'm going to call mu dash X is the new credit of X, and mu dash Y is the new credit of Y after I make display. So the cost is going to be mu dash X plus mu dash Y minus mu of X minus mu of Y. Why am I doing it this way? I'm saying that the cost of display is going to be the current value of the bank account of X after I make it the root, and this is mu dash X. So that will be the new balance after I have pushed X upward. Now remember, pushing X upward actually saves us some money, okay? And pushing Y downward are taking away money from us, because now we have to pay that if we're going to push y again up. So the total cost is going to be the final balance of x, which is mu dash x, plus the final balance of y, which is mu dash y, minus what they started with, because there were some dollars in the bank account for x. And to push x up, I will add to x's account some money I'm saving. And it will cost me something to actually push it upward, but I'm also saving something. So there is a new balance for x, which is mu dash x. The same thing for y. To push y down, now y has now a new balance, which is mu dash y. The adding up mu dash x and mu dash y will result in the total amount of dollars that currently exist in both balances. But that will not be the cost. To get the cost, it's going to be the difference between the old balances and the new balances. So I'm adding up the new balances for x and y, which is the mu dash x and the mu dash y, and I'm subtracting from it the old balances, which is mu of x and mu of y. This difference between the new balances and the old balances is actually the cost of this operation. Okay? Now, since y decreases in size, mu dash y will always be less than or equal mu dash x. Let's think about this a little bit. How are we actually calculating the bank balance? We are calculating it from the number of elements in the subtree rooted at x in the case of x, and in the subtree rooted at y in the case of y. Y will decrease in size because the number of elements below it has decreased. Initially y was the root, and it had x underneath it as well as all of a, all of b, all of c. When we rotate x through y, y now has all of b, all of c, but not all of a and not x. So y has decreased in size in terms of the total number of elements, and consequently the total height underneath it has decreased, and consequently mu dash y has decreased or is less than what it initially had, which is mu y. Similarly, we could argue that now since x is the root, it has to be bigger than or equal to mu dash y. Okay? So mu dash y is generally either less than or equal to, in the best case, to mu dash x. And mu dash x has to be greater than, or in the worst case, equal to mu dash y. Okay? Now, since x and y has exchanged positions, mu dash x, the new bank credit of x, has to be the same as the old bank credit of y. So mu dash x is equal to mu y. Now, as a consequence, the cost of operation is at most mu dash x minus mu x. Okay? Yani in the largest difference you will get is between the bank balances of the new x and the bank balance of the old x. That's the largest difference. Okay? Now, since x increases in height, mu dash x minus mu x must be a positive value, or in other words, a positive bank balance, because I have just pushed x upward, and when I push x upward, I actually made the whole tree underneath it, so there are more elements now than before, so the bank balance must have increased. Okay? Now, the cost is bounded by 3 mu dash x minus mu of x. The question is, where did I get the 3 from? And I will leave that for you as an exercise, or you can ask me about it in the live sessions. It's really a matter of substitution here with mu dash x and mu y. Okay? So you can actually figure that out on your own, hopefully. The question is now, can we pay that amount? And the answer is simple, yes, because we initially had a bank balance of mu of x, and when we increased the height of x by making it now the root, our gain from that is mu dash x. So we will add mu dash x to mu of x to be the total sum we have in the bank now. I'm just going to give you a hypothetical example. Let's say x bank balance was $5. When you move up the x, the bank balance increases. You're going to add to this $5 another amount because now you have the height increased by one level. So if you've added up $5 gradually by moving x upward along the progression of the lifetime of the data structure, now when you move it even further up, you add even further dollars. So if mu dash x is going to have any effect, it's going to be adding more money to the bank balance, because now there are more elements underneath x, and consequently the height will be more, and consequently the dollars will even increase more. So we can definitely afford mu dash x minus mu x, which is going to be just the cost of one operation, 3 times that. Okay, so we can definitely afford 3 times the cost of the moving up x one level. Okay, so we can pay for this for sure. In fact, we have more dollars than that in the bank. Now let's look at the next case. The next case is the zigzag. Notice that we're going to do the following. We are going to rotate the y through the z first, and then the x through the y. Okay? So here I have 3 nodes that are changing their bank balance. The final cost of my change is the new cost of x, which is mu dash x, plus the new cost of y, which is mu dash y, plus the new cost of z, which is mu dash z, minus the old cost of x, or the old balance of x, which is mu of x minus mu of y minus mu of z. In other words, to figure out how much money I need, I will sum the new balances of x, y, and z, which is designated by the dash. I will sum these new balances, and I will subtract from them the old balances. So new minus old will give me how much I need to spend to do these operations. Okay? Now, I have here an equation that has many unknowns. So I will try to reduce my number of unknowns by the following observation. Mu dash x is the same as mu of z, because it's going to be the same height and the same number of entries. Okay? Now, because ultimately x becomes the root, and historically in the first figure to the left above, z was the root. So the new bank balance of x, mu dash x, has to be exactly the same as the old bank balance of z. Because again, we're calculating it based on the number of nodes and on the height. So I can replace the following. Wherever there is mu of z, I can replace it with mu dash x. Okay? So this becomes mu dash y plus mu dash z plus mu of x minus mu of y. Okay? So we have terms lost here, or gone. And then I can group them. Mu dash y minus mu dash x plus mu dash z minus mu dash y. Okay? Now, notice that mu dash x is greater than mu dash z. Mu dash x is the new balance of x, which is at the top now of the tree, so it has to be bigger than anything else. mu dash z is at the bottom now 2 levels away from the root, and mu dash y is 1 level away from the root. Okay, and mu dash x is less than, mu x is less than mu y. So historically I started with x 2 levels away and y was 1 level away. So at most this term I'm looking at evaluates to 2 mu dash x minus mu x. Now this is interesting because what I'm saying is at most the cost of this operation is going to be the difference between the new balance of x and the old balance of x 2 times. And the question is, do I have this in the bank? Again, we are going to follow the same logic as in the first case. Historically x was 2 levels down. If I push it up, I'm actually accumulating balances in the bank. So if I keep pushing it up all the way to become the root, mu dash x plus mu of x must be greater than 2 mu dash x minus mu x. Okay, this is a simple mathematical fact, which again you can plug in the values here in the formula and come up with the same conclusion I'm describing here. Now the third case, which is zigzag, is going to all turn to be the same as zigzag. It's going to be 2 mu dash x minus mu of x. And here are the summary of the 3 cases in terms of the cost that I have calculated to find out whether I have this in the bank or not. And I have here an observation not related to how we computed all of this, but about the nature of these equations we're looking at. Everything we've done up to now, hopefully you're following what's going on. But where is the log appearing? What I am doing is I am working out the bank balances as I explained, node x, and then I come up with an equation like this that tells me, at most I need this to do this specific operation, whether it's zigzag or zigzag, okay, or the simple case of rotating through the root. But the question is, did I prove anything? And the answer is actually yes. Because in these 3 equations, when you look at them, what is each one resolves to? It's the floor of log of the subtree rooted at x. So the first one is 2 log minus log. The second one is 2 log minus log. The third one is 3 log minus log. So they're all in log. Okay? I have proven that I have enough money at least in the bank to pay for this. Each one of those 3 cases, and in each one of those 3 cases, the cost is expressed in log. So the performance is in log. And this is why we say it's amortized log n. Okay? I hope this is clear. Now, to conclude splay trees, I must tell you that they are very, very popular in many network applications, including network routers and proxies and firewalls and gateways. In fact, it's guaranteed that the router you have at home, whether from TE Data or Vodafone or whatever, will have a splay tree. So it is used in all kind of network applications because of this ability to remember the history and in the same time to search very fast in log n in the stored data in the splay tree. So I will leave this explanation for you along with the next slide that tells you how this could be actually used. Just to give you an idea of an application of splay trees. They are very interesting data structures, but what I also would like to stress on is that they are very widely used in certain areas of technology, specifically network technologies. And you can read this on your own. You will have the lecture slides posted. This is the references for today's lecture, the splay tree. Goodrich and Tamasea, they do a very good job in actually explaining splay trees. And there is an additional example that you will see in the tutorial for disjoint sets. It's another data structure that's also popular, that's also doing amortization. And I've included here the link for Goodrich and Tamassia that covers disjoint sets.